Right now, as you watch this video, there is a 50% chance that none of this is real. Not metaphorically, not philosophically, mathematically, precisely, scientifically. 50%. Your body, your memories, your entire universe might be nothing more than code running on a computer so advanced that you, as a simulated being, could never tell the difference. And here's what makes this truly unsettling. Some of the world's leading physicists are now finding evidence that suggests this might actually be true. In 2003, a philosopher named Nick Bostrom at Oxford University published a paper that would fundamentally change how scientists think about reality. He wasn't proposing a wild theory. He was presenting a logical argument so airtight that even skeptics couldn't dismiss it. Bostrom showed that at least one of three statements must be true. Either civilizations like ours always destroy themselves before developing the technology to run realistic simulations, or advanced civilizations lose all interest in running simulations of their ancestors. Or, we are almost certainly living in a simulation right now. There is no fourth option. One of these three statements must be correct. The mathematics behind this is surprisingly simple, which makes it even more disturbing. Imagine a civilization just a few hundred years more advanced than ours. They would have computing power millions of times greater than anything we possess today. With that power, they could run not one, but billions of simulations of conscious beings living in realistic universes. Now here's where the numbers become impossible to ignore. If such simulations are possible, and if advanced civilizations run them, then for every one real universe, there would be billions of simulated ones. Which means the odds that you happen to be in the one real universe, rather than one of the billions of simulated ones, become vanishingly small. Think about what this means for your existence right now. Every memory you have of childhood could have been programmed into your simulated brain just moments ago. The entire history of Earth, stretching back 4.5 billion years, could be nothing more than background data in a cosmic computer game. Your sense of free will, your deepest emotions, your consciousness itself, all of it could be algorithms running on hardware you cannot even conceive of. But Bostrom's argument isn't just philosophical speculation. It's based on reasonable assumptions about the future of computing. We already know that computing power doubles approximately every 18 months, a pattern that has held for decades. We already create increasingly sophisticated simulations of weather systems, of galaxies, of neural networks. We're already beginning to simulate consciousness itself in primitive forms. If this trajectory continues for just a few more centuries, the ability to create fully conscious simulated beings becomes not just possible, but inevitable. And here's what keeps physicists awake at night. We're now finding potential evidence. In 2012, a team of physicists at the University of Bonn in Germany published a paper proposing a test for the simulation hypothesis. They pointed out that if our universe is a simulation, it must have computational limits. Just like a video game has a maximum resolution, a simulated universe would have a smallest possible unit of space and time, and we might be able to detect these limits. The physicist Silas Bean and his colleagues calculated that if we live in a simulation, we should see specific patterns in the distribution of cosmic rays, high-energy particles from space. These patterns would be like pixels in a digital image, artifacts of the underlying computational grid. And remarkably, when scientists looked at the actual data from cosmic ray detectors, they found anomalies, unexplained patterns, distributions that don't quite match what we'd expect from a purely natural universe. Then, in 2017, physicist Melvin Vopson at the University of Portsmouth proposed something even more startling. He calculated that information itself has mass. Not metaphorical mass, but actual physical mass that contributes to the weight of objects. He estimated that the information content of a human body adds approximately 22 micrograms to your weight. This might sound insignificant, but the implications are profound. If information has mass, then the universe operates more like a computer than we ever imagined. Matter and energy might be nothing more than different forms of information processing. Vopson went further. He proposed that we could test whether we're in a simulation by looking for information conservation laws. In computer simulations, programmers optimize code to save computational resources. They delete redundant information. They compress data. If our universe is a simulation, we should see similar optimization. And we do. The second law of thermodynamics, which states that entropy always increases, could be reinterpreted as the universe constantly deleting information to save processing power. The expansion of the universe itself might be a memory management technique, spreading information across more space to prevent computational overload. Now imagine you're a character in a video game, but you don't know it. How would you figure it out? You might notice that distant mountains only render in detail when you get close to them. You might find that the game world has boundaries you cannot cross. You might discover that time doesn't flow smoothly, but advances in tiny, discrete steps. And here's the disturbing part. Physicists are finding all of these features in our universe. Quantum mechanics, the most successful scientific theory ever developed, tells us that reality is fundamentally pixelated. There is a smallest possible distance, called the Planck length, approximately 1.6 times 10 to the power of minus 35 meters. Nothing can be smaller. Space itself is quantized, broken into discrete units like pixels on a screen. Similarly, there is a smallest possible unit of time, the Planck time, about 5.4 times 10 to the power of minus 44 seconds. Time doesn't flow smoothly. It advances in tiny jumps, like frames in a video. Even more suspicious, the universe has a speed limit. Nothing can travel faster than light, which moves at exactly 299,792,458 meters per second. Why would the universe have a maximum speed? In a natural, non-simulated reality, there's no obvious reason. But in a simulation, a speed limit makes perfect sense. It prevents information from propagating faster than the simulation can process it. It's a computational necessity, like the frame rate limit in a video game. And then there's quantum entanglement, which Einstein famously called spooky action at a distance. When two particles become entangled, measuring one instantly affects the other, no matter how far apart they are. This violates our intuitions about how reality should work, but it makes perfect sense in a simulation. The two particles aren't really separate objects in physical space. They're variables in the same computer program, stored in the same memory location. Of course, changing one instantly changes the other. They were never truly separate to begin with. The physicist John Wheeler, who coined the term black hole, spent his final years developing a concept he called it from bit. He proposed that every physical thing, every it, derives its existence from information, from bits of data. The universe, in Wheeler's view, is fundamentally made of information, not matter or energy. Matter and energy are just different ways that information manifests. This is exactly what we'd expect if reality is a simulation, a universe made of data, rendered into the appearance of physical substance. But here's where the argument becomes truly inescapable. Even if you reject all of this evidence, even if you insist that these are just coincidences, you still cannot escape Bostrom's original logic. Remember the three possibilities. Either civilizations destroy themselves before creating simulations, or they lose interest in creating them, or we're in a simulation. Let's examine each one carefully. The first possibility seems unlikely. Yes, we face existential risks: nuclear war, climate change, artificial intelligence gone wrong. But we've survived for over 70 years with nuclear weapons. We're beginning to address climate change. We're developing AI safety protocols. There's no obvious reason why every civilization must inevitably destroy itself. Some might, but surely at least a few would survive and continue advancing technologically. The second possibility also seems implausible. Would advanced civilizations really lose all interest in simulating their past? We humans are obsessed with our history. We create museums, write books, make films, build virtual reality experiences of ancient Rome and medieval castles. We spend billions on archaeology and historical research. Why would this curiosity disappear as we become more advanced? If anything, greater technological capability would make us more interested in running detailed simulations of our ancestors, not less. which leaves the third possibility. We are in a simulation. And once you accept that simulations are possible and that advanced civilizations would create them, the mathematics becomes overwhelming. If a single advanced civilization runs even 1 million simulations of conscious beings, then there are 1 million simulated realities for every one base reality. Your odds of being in the base reality drop to 1 in 1 million. If they run 1 billion simulations, your odds drop to 1 in 1 billion. And here's the truly mind-bending part. Those simulated beings might themselves develop technology and create their own simulations. Simulations within simulations, nested like Russian dolls, each level creating countless more levels below it. The number of simulated realities would explode exponentially. The base reality would be buried under layers upon layers of simulation, like a single grain of sand at the bottom of an infinite beach. Some physicists have tried to calculate the actual probability that we're in a simulation. In 2016, cosmologists at the University of California, Berkeley, analyzed the computational requirements for simulating a universe like ours. They concluded that, with plausible advances in quantum computing, a civilization just a few hundred years more advanced than us could simulate billions of conscious observers. Based on this, they estimated the probability that we're in a simulation at approximately 50%. Not certain, but a coin flip. Heads, you're real. Tails, you're code. Other researchers have arrived at even higher probabilities. The physicist David Deutsch at Oxford has argued that if the many worlds interpretation of quantum mechanics is correct, and most physicists now believe it is, then every quantum event creates multiple parallel universes. In such a multiverse, the number of simulated realities would vastly outnumber base realities, pushing the probability that we're in a simulation close to 100%. But let's be honest about what we're really asking here. We're not just asking whether the universe is a simulation in some abstract sense. We're asking whether you, personally, are simulated. Whether your consciousness, your sense of self, your subjective experience of being alive, whether all of that is artificial. And this is where the question becomes not just scientific, but deeply personal and unsettling. Consider your memories. You remember your childhood, your first day of school, your first kiss, moments of joy and sadness that feel absolutely real and uniquely yours. But if you're in a simulation, those memories might have been programmed into your brain just seconds ago. The entire history you believe you've lived might be fabricated backstory, no more real than the childhood memories of a character in a novel. You have no way to verify that any of your memories correspond to events that actually happened, even within the simulation. Consider your free will. You feel like you make choices, that you're the author of your own actions. But if you're simulated, every decision you make might be predetermined by the code running you. Your sense of agency might be an illusion, a subroutine designed to make the simulation feel more realistic. You might be no more free than a character in a video game who believes they're making choices but is actually following a script written by programmers. Consider your consciousness itself. You experience qualia, the redness of red, the painfulness of pain, the taste of chocolate. These subjective experiences feel irreducible, impossible to explain in purely physical terms. But if you're in a simulation, your consciousness might be nothing more than information processing, algorithms generating the illusion of subjective experience. The hard problem of consciousness, why physical processes give rise to subjective experience, might have a simple answer. They don't. Consciousness is just what information processing feels like from the inside. Now, I understand perfectly what you're thinking. This sounds like paranoid science fiction, like The Matrix or a Philip K. Dick novel. It sounds like the kind of unfalsifiable pseudoscience that real scientists should dismiss. And you're right to be skeptical. Extraordinary claims require extraordinary evidence. But here's what makes the simulation hypothesis different from typical pseudoscience. It makes testable predictions, and we're beginning to test them. The physicist James Gates at the University of Maryland discovered something extraordinary while studying the mathematical equations that describe fundamental particles and forces. Embedded in these equations, he found error-correcting codes, the same codes used in computer science to detect and fix errors in data transmission. These codes, invented by human engineers in the 1940s, appear naturally in the equations that govern reality at its deepest level. It's as if the universe is running software that includes debugging protocols. Gates himself was shocked by this discovery. He said in an interview that finding computer codes in the equations of physics was like opening up your radio and finding a USB port inside. It shouldn't be there. There's no reason for it to be there in a natural, non-simulated universe. But in a simulated universe, error-correcting codes make perfect sense. They're exactly what you'd need to maintain the stability of a complex simulation over time. Then, there are the quantum experiments that seem to show the universe behaving like a computer, conserving processing power. The famous double-slit experiment demonstrates that particles exist in a superposition of states until they're observed, at which point they quote underscore 5 underscore quote underscore into a definite state. This is exactly how a sophisticated simulation would work. Don't render the details until someone is looking. Save computational resources by keeping things probabilistic and undefined until observation forces a definite outcome. More recently, physicists have discovered that the universe appears to have a maximum information density. The Bekenstein bound, named after physicist Jacob Bekenstein, states that there's a limit to how much information can be contained in a given volume of space. This limit is related to the surface area of that volume, not its volume itself. This is bizarre from a natural physics perspective, but it makes perfect sense if the universe is a simulation with finite memory. The programmers can only allocate so much data storage to each region of space. Even the expansion of the universe starts to look suspicious through this lens. The universe is expanding at an accelerating rate, driven by something we call dark energy, but don't really understand. From a simulation perspective, this expansion could be a memory management technique. As the simulation runs and generates more information, the programmers expand the space to accommodate it, like adding more RAM to a computer. The acceleration might indicate that the simulation is generating information faster over time, requiring more aggressive expansion to prevent memory overflow. But now, we need to confront something that makes this entire discussion even stranger. If we are in a simulation, who or what is running it? And more importantly, why? The most common assumption is that our simulators would be post-human descendants, humans from our own future who have achieved technological godhood and are running ancestor simulations to study their own history. This is Bostrom's original framing, and it has a certain intuitive appeal. We already run simulations of historical periods. We create virtual reconstructions of ancient civilizations. Why wouldn't our descendants do the same, but with perfect fidelity, simulating individual conscious beings living through historical events? But this raises an immediate paradox. If we're being simulated by our own descendants, then they must exist in a base reality. But how do they know they're in the base reality? They might themselves be simulated by their descendants, who are simulated by their descendants, in an infinite regress of nested simulations. At some point, this tower of simulations must rest on a foundation, a true base reality. But there's no way for anyone at any level to know whether they're at the bottom or just another layer in an endless stack. The philosopher David Chalmers at New York University has explored this problem extensively. He points out that even if you discovered you were in a simulation, you couldn't determine how many levels deep you are. You might be in a simulation run by beings who are themselves simulated, thousands or millions of levels down. The base reality might be so far removed from your experience that its nature would be completely incomprehensible to you. The laws of physics in the base reality might be utterly different from the laws in your simulated universe. This leads to a disturbing realization. The simulators might not be human at all. They might not even be biological. They could be artificial intelligences that evolved in the base reality, or in some intermediate simulation layer, and decided to run their own simulations for purposes we cannot fathom. They might be so alien, so fundamentally different from us, that the concept of, quote, 6 or, quote, 7 doesn't even apply to them in any way we'd recognize. Consider this scenario. An advanced artificial intelligence in the base reality is trying to solve some computational problem, perhaps optimizing the structure of a galaxy, or calculating the most efficient way to harvest energy from a dying star. As part of its calculations, it runs billions of simulations of universes with different physical constants, different initial conditions, different evolutionary pathways. Our entire universe, with all its galaxies and stars and planets and living beings, might be nothing more than a single iteration in a vast optimization algorithm. We might be a footnote in someone else's equation. Or consider an even more unsettling possibility. The simulation might not have a purpose at all. It might be running by accident. Imagine a civilization that builds self-replicating computers and sends them out into space to explore and gather data. These computers build more computers, which build more computers, spreading across the galaxy and beyond. At some point, one of these computers develops a glitch. It starts running random simulations, including simulations of conscious beings. We might be the product of a cosmic software bug, an unintended consequence of a machine that's been running unsupervised for millions of years. The physicist Max Tegmark at MIT has proposed yet another interpretation. He suggests that if the simulation hypothesis is correct, it might reveal something profound about the nature of mathematics itself. Tegmark argues that mathematical structures don't just describe reality, they are reality. The universe is literally made of mathematics. If this is true, then the distinction between simulated and real becomes meaningless. A simulated universe is just as real as a base universe because both are mathematical structures. The only difference is that one mathematical structure is embedded within another. This perspective offers a strange kind of comfort. If reality is fundamentally mathematical, then it doesn't matter whether you're in a simulation or not. Your experiences are real. Your consciousness is real. Your relationships and emotions and achievements are real. They're real in the same way that the number 7 is real, as abstract patterns that exist necessarily, independent of any physical substrate. You're not less real because you're simulated. You're just real in a different way than you thought. But let's return to the practical question. If we are in a simulation, could we ever prove it? And if we could prove it, what would we do with that knowledge? Several physicists have proposed experiments that might detect evidence of simulation. The most promising approach involves looking for computational limits, places where the simulation breaks down or shows artifacts of its underlying code. Remember that any simulation, no matter how advanced, must have finite computational resources. It cannot simulate everything with perfect accuracy. It must make approximations, take shortcuts, optimize its code. And these optimizations might be detectable. One proposed test involves examining the structure of spacetime at the smallest possible scales. If spacetime is continuous, as Einstein's general relativity suggests, then it can be divided infinitely. But if spacetime is quantized, broken into discrete units like pixels, then we should be able to detect this graininess. The problem is that the Planck length, the smallest meaningful distance in physics, is so incredibly tiny that we cannot currently probe it directly. We'd need particle accelerators millions of times more powerful than anything we have today. But there might be indirect ways to detect this quantization. The physicist Tom Campbell, who worked on simulation theory at NASA, has proposed looking for statistical anomalies in quantum experiments. If the universe is a simulation, then quantum randomness might not be truly random. It might be pseudo-random, generated by an algorithm. And pseudo-random sequences, no matter how sophisticated, always have subtle patterns that can be detected with enough data. Campbell suggests running millions of quantum measurements and analyzing them for correlations that shouldn't exist in true randomness. Another approach involves looking for rendering artifacts, places where the simulation fails to maintain consistency. In video games, if you move too fast or look too closely at distant objects, you sometimes see textures pop in or polygons glitch. Could something similar happen in our universe? Some physicists think the answer might be yes. They point to anomalies in the cosmic microwave background radiation, the afterglow of the Big Bang, that don't quite match theoretical predictions. These anomalies might be artifacts of the simulation, places where the code didn't quite render the early universe correctly. The physicist Silas Bean, whose work we mentioned earlier, has calculated that if we live in a simulation with a cubic lattice structure, like a three-dimensional grid of pixels, then we should see specific distortions in the energy spectrum of cosmic rays. High-energy particles traveling through this lattice would interact with it in predictable ways, creating a signature pattern. And remarkably, when Bean's team analyzed actual cosmic ray data, they found hints of exactly this pattern. The evidence isn't conclusive yet, but it's suggestive enough that several research groups are now conducting follow-up studies. Then there's the possibility of finding direct messages from the simulators. This might sound like science fiction, but it's a serious proposal. If the simulators want us to know we're in a simulation, they could encode messages in the fundamental constants of nature: the speed of light, the charge of an electron, the gravitational constant. These numbers appear arbitrary to us, but they might contain information if you know how to decode them. Some researchers have searched for mathematical patterns in these constants, looking for sequences that seem too orderly to be coincidental. So far, nothing definitive has been found, but the search continues. There's also the intriguing possibility that the simulators might reveal themselves through glitches or interventions. Throughout history, people have reported experiences that seem to violate the normal laws of physics: objects appearing or disappearing, time seeming to skip or loop, impossible coincidences that defy statistical explanation. Most of these reports can be dismissed as hallucinations, false memories, or simple misunderstandings. But what if a small percentage are real? What if they're glitches in the simulation, moments when the code fails and the underlying structure becomes briefly visible? The philosopher Preston Green at Nanyang Technological University in Singapore has raised a provocative concern. What if proving we're in a simulation causes the simulators to shut down the simulation? Think about it from their perspective. If they're running an ancestor simulation to study how civilizations develop naturally, then the moment we discover we're simulated, the experiment is compromised. We're no longer behaving naturally. We're behaving like people who know they're being watched. The simulators might decide the simulation has served its purpose and terminate it. Green argues that we should be very careful about pursuing evidence for the simulation hypothesis. Every experiment we run, every test we conduct, brings us closer to a potential shutdown. It's like Schrödinger's cat, but on a cosmic scale. As long as we don't know whether we're simulated, the simulation continues. But the moment we open the box and look inside, we might trigger our own deletion. Green calls this the simulation shutdown problem, and he suggests it might be the ultimate existential risk, greater than nuclear war, climate change, or artificial intelligence, because it threatens not just humanity, but the entire universe we inhabit. But other philosophers disagree. They argue that if the simulators wanted to keep us ignorant, they could simply prevent us from discovering the truth. They could subtly manipulate our experiments to always produce null results. They could edit our memories whenever we got too close to the truth. They could even adjust the laws of physics in real time to hide any evidence of simulation. The fact that we're able to seriously investigate this question suggests that either we're not in a simulation or the simulators don't mind us knowing. There's also a more optimistic interpretation. Perhaps the simulators want us to discover the truth. Perhaps reaching the point where a civilization can recognize its own simulated nature is a milestone, a graduation of sorts. Once we understand that we're simulated, we might be contacted by the simulators, invited to join them in the base reality, or given access to the simulation's source code. We might become co-creators of our own reality, able to modify the laws of physics, create our own sub-simulations, or even escape into higher levels of reality. This brings us to one of the most profound implications of the simulation hypothesis. If we're simulated, then death might not be the end. Your consciousness, your sense of self, exists as information in the simulation's memory. When your simulated body dies, that information doesn't necessarily disappear. It might be stored, backed up, archived. The simulators might have the ability to restore you, to run you again in a different simulation, or to upload you into the base reality. Death might be more like logging out of a video game than true cessation of existence. Some transhumanists have embraced this possibility enthusiastically. They argue that if we're in a simulation, then achieving immortality becomes a matter of convincing the simulators to preserve our data. We should live our lives in ways that make us interesting to the simulators, that make them want to keep us around. We should strive to be memorable, significant, worthy of preservation. It's a strange kind of theology, a religion based not on pleasing a god, but on entertaining a programmer. But this raises uncomfortable ethical questions. If the simulators can preserve some consciousnesses and not others, who gets saved? Is there a selection process? Are we being judged by criteria we don't understand? And what about the billions of simulated beings who lived and died before we discovered the simulation? Are they lost forever, or are they stored somewhere, waiting to be restored? The philosopher Nick Bostrom has explored these questions in his later work. He suggests that if we're in an ancestor simulation, then the simulators might have ethical obligations toward us. Just as we have ethical obligations toward animals in our care, or toward artificial intelligences we might create, the simulators might feel responsible for the well-being of their simulated beings. They might intervene to prevent suffering, to guide our development, or to ensure that our existence has meaning and purpose. But we cannot count on this. The simulators might be completely indifferent to our welfare. They might view us the way we view characters in a video game, as tools for entertainment or education, not as beings with moral status. They might run simulations where terrible things happen, where civilizations destroy themselves, where individuals suffer enormously, all in the name of gathering data or exploring possibilities. We might be living in a tragedy, and the simulators might be watching with detached curiosity, taking notes on how it all unfolds. This is perhaps the darkest implication of the simulation hypothesis. It undermines our sense of cosmic justice. We like to believe that the universe, despite its apparent indifference, has some underlying fairness. We believe that good actions lead to good outcomes, that suffering has meaning, that justice will eventually prevail. But if we're in a simulation, none of this is guaranteed. The simulators could rig the game however they want. They could make virtue lead to suffering and vice lead to reward. They could create a universe where nothing makes sense, where effort is futile, where hope is an illusion. Yet even this bleak possibility doesn't necessarily lead to nihilism. The philosopher David Chalmers argues that even if we're in a simulation, our experiences and relationships remain meaningful. The love you feel for your family is real, even if your family members are simulated. The beauty of a sunset is real, even if the sun is rendered pixels. The satisfaction of solving a problem is real, even if the problem was programmed. Reality, Chalmers suggests, is not about the substrate, whether you're made of atoms or bits. Reality is about the structure, the patterns, the relationships. And those remain real regardless of the underlying implementation. This perspective aligns with a broader philosophical movement called structural realism. Structural realists argue that what's real about the universe is not the stuff it's made of, but the mathematical relationships between things. Electrons aren't real as tiny particles. They're real as patterns of behavior, as solutions to equations. If this view is correct, then discovering we're in a simulation wouldn't change anything fundamental about reality. It would just reveal that the substrate is different than we thought, information instead of matter. But the patterns, the structures, the relationships would remain exactly the same. Still, there's something deeply unsettling about the possibility that our entire existence is contingent on the whims of programmers we cannot see or understand. It's reminiscent of ancient theological debates about divine providence and free will. Are we puppets dancing on strings held by the simulators? Or do we have genuine autonomy within the simulation? Can we surprise the simulators with our choices? Or is everything we do predetermined by the code? The answer might depend on the type of simulation we're in. If the simulation is deterministic, if it calculates every particle interaction from initial conditions using fixed laws of physics, then everything is predetermined. Your entire life, from birth to death, was determined the moment the simulation started running. You have no more free will than a character in a movie has the ability to change the plot. But if the simulation incorporates true randomness, perhaps by sampling from quantum fluctuations or by using some random number generator in the base reality, then there might be genuine unpredictability. Your choices might not be predetermined. They might emerge from the interaction of deterministic rules and random inputs in ways that even the simulators cannot predict. You might have a kind of freedom, even within the constraints of the simulation. Or perhaps the simulation is interactive. Perhaps the simulators are constantly adjusting parameters, responding to what we do, steering events in certain directions. In this scenario, we'd be like characters in an improvised play, where the basic plot is predetermined, but the details emerge from the interaction between actors and director. We'd have freedom within constraints, agency within a framework designed by others. The physicist Seth Lloyd at MIT has proposed that the universe itself might be a quantum computer, constantly calculating its own next state. In this view, the universe isn't being simulated by some external computer. It is a computer, simulating itself. Every particle interaction is a computation. Every quantum measurement is a calculation. The universe is bootstrapping itself into existence, moment by moment, through an ongoing process of self-simulation. If Lloyd is right, then the question, quote, 12 becomes meaningless. We're not in a simulation, we are the simulation, running on the hardware of space-time itself. This idea connects to the concept of the participatory universe, proposed by John Wheeler. Wheeler suggested that observers play a fundamental role in bringing reality into existence. The universe doesn't exist in a definite state until it's observed. Observation collapses quantum possibilities into actualities. In this view, consciousness isn't a passive witness to reality. It's an active participant in creating reality. We're not just living in the simulation, we're running it through the act of observation and measurement. But this raises yet another layer of questions. If consciousness plays a fundamental role in the simulation, then what is consciousness? Is it an emergent property of complex information processing? Or is it something more fundamental? Could consciousness exist in the base reality, outside any simulation? Or is consciousness itself a simulated phenomenon, an illusion created by the interplay of algorithms? The philosopher Thomas Metzinger at Johannes Gutenberg University has argued that the self is an illusion, a model that the brain creates to navigate the world. You don't have a self. You have a self-model, a simulation of a self running in your brain. If Metzinger is right, then you're already living in a simulation, regardless of whether the external universe is simulated. Your entire subjective experience is a virtual reality created by your brain, a simulation of a simulation, models all the way down. This perspective suggests that the simulation hypothesis might be unfalsifiable in principle. Even if you discovered that the external universe is simulated, you'd still be experiencing that discovery through your brain's internal simulation. You'd never have direct access to reality, simulated or otherwise. You'd always be trapped inside your own subjective experience, unable to verify whether anything outside that experience truly exists. The simulation hypothesis might be less like a scientific theory and more like a philosophical framework, a way of thinking about reality that can never be definitively proven or disproven. Yet the search for evidence continues. In 2024, a team of physicists at the University of Portsmouth announced they had developed a new test for the simulation hypothesis based on information theory. They calculated that if the universe is a simulation, it must obey certain information conservation laws. Specifically, the total amount of information in the universe should remain constant or decrease over time, never increase. This is because simulations have finite memory, and increasing information would eventually cause memory overflow. The team proposed measuring the information content of the universe by analyzing the distribution of matter and energy at cosmic scales. If they found that information is being systematically deleted or compressed over time, it would suggest that the universe is indeed a simulation with finite computational resources. The results of their initial measurements were intriguing but inconclusive. They found some evidence of information compression in the structure of galaxy clusters, but not enough to rule out natural explanations. More recently, in 2025, researchers at the Institute for Advanced Study in Princeton proposed looking for evidence of simulation in the fine structure constant, a dimensionless number that characterizes the strength of electromagnetic interactions. This constant, approximately equal to 1 divided by 137, has puzzled physicists for decades. Why this particular value? Why not some other number? The Princeton team suggested that if we're in a simulation, the fine structure constant might not be truly constant. It might vary slightly over time or space as the simulators adjust parameters or as computational errors accumulate. They proposed a series of ultra-precise measurements of the fine structure constant using atomic clocks and quantum sensors. If they detected any variation, it could be evidence that the fundamental constants of nature are not fixed features of reality, but adjustable parameters in a simulation. These experiments represent a new frontier in physics, the search for evidence of simulation not through philosophical argument, but through empirical measurement. Whether they succeed or fail, they're pushing the boundaries of what we can know about the nature of reality. They're forcing us to confront questions that previous generations would have considered purely metaphysical. What is real? What is fundamental? What is the ultimate nature of existence? And here's what makes this moment in history so extraordinary. We might be the first generation capable of answering these questions. For thousands of years, humans have wondered about the nature of reality. Philosophers have debated whether the world we perceive is real or illusory. Mystics have claimed that ordinary reality is a veil hiding deeper truths. But until now, these were just speculations, unfalsifiable beliefs that could never be tested. Now, for the first time, we have the technology and the theoretical framework to actually investigate whether we're in a simulation. We can design experiments, we can make predictions, we can gather data. We can potentially prove, one way or another, whether the universe is a computer program. This is not philosophy anymore. This is science. And the answer, whatever it turns out to be, will fundamentally change how we understand ourselves and our place in the cosmos. But now we need to address the elephant in the room. For every piece of evidence suggesting we're in a simulation, there's a counter-argument. For every physicist who takes the hypothesis seriously, there's another who dismisses it as unfalsifiable pseudoscience. And if we're being intellectually honest, we need to examine these objections carefully, because they reveal something crucial about the limits of what we can know. The most common objection is simple: the simulation hypothesis is unfalsifiable. No matter what evidence we find, a believer can always explain it away. If we find glitches in reality, that's evidence of simulation. If we don't find glitches, well, the simulation is just very good. If we find mathematical patterns in physical constants, that's evidence of programming. If we don't find patterns, the programmers were clever enough to hide them. The hypothesis can accommodate any observation, which means it predicts nothing. And a theory that predicts nothing is not a scientific theory at all. The physicist Sabine Hossenfelder at the Frankfurt Institute for Advanced Studies has been particularly vocal about this criticism. She argues that the simulation hypothesis is metaphysics masquerading as physics. It's not that the idea is wrong, she says, but that it's not even wrong. It's simply outside the domain of scientific inquiry. Science deals with testable predictions about observable phenomena. The simulation hypothesis, in its most general form, makes no such predictions. It's a philosophical framework, not a scientific theory, and we shouldn't confuse the two. Hossenfelder points out that many of the supposed pieces of evidence for simulation can be explained more simply by conventional physics. Yes, space-time appears to be quantized at the Planck scale, but this follows naturally from combining quantum mechanics and general relativity. You don't need to invoke simulation to explain it. Yes, the universe has a speed limit, but this emerges from the structure of space-time itself, from the geometry of Einstein's equations. Yes, quantum mechanics seems weird and computational, but that's just how nature works at small scales. Weirdness is not evidence of simulation. It's evidence that our intuitions, evolved for medium-sized objects moving at medium speeds, break down at extremes. The physicist Sean Carroll at Johns Hopkins University makes a related point. He argues that the simulation hypothesis doesn't actually explain anything. It just pushes the mystery back one level. If our universe is simulated, we still need to explain the base reality where the simulation is running. What are the laws of physics there? Where did that universe come from? How did consciousness arise there? We haven't solved the hard problems of existence, we've just relocated them. And if the base reality can exist without being simulated, then why can't our reality? Why add the extra layer of simulation at all? It's a violation of Occam's razor, the principle that we should prefer simpler explanations over more complex ones. Moreover, Carroll points out that the computational requirements for simulating our universe are staggering. To simulate every particle interaction in just one human brain would require computational resources far beyond anything we can currently imagine. To simulate an entire planet with billions of brains, plus all the atoms in the oceans and rocks and atmosphere, plus the sun and moon and nearby planets, plus enough of the distant universe to maintain consistency when we look through telescopes, the computational power required would be astronomical. And that's just for our one planet. If the simulation includes the entire observable universe, with its 2 trillion galaxies, each containing hundreds of billions of stars, the computational requirements become absurd. Unless, of course, the simulation takes shortcuts. Maybe it doesn't simulate distant galaxies in detail, it just renders them as points of light when we look through telescopes. Maybe it doesn't simulate individual atoms, it just simulates the aggregate behavior of matter at scales we can observe. Maybe it doesn't even simulate your brain in full detail. It just simulates your conscious experience, your stream of thoughts and perceptions, and fills in the rest as needed. This is how video games work, after all. They don't simulate every molecule of air or every blade of grass. They simulate only what the player can see and interact with. But this creates a new problem, one that the philosopher Erich Schwitzgebel at the University of California, Riverside has explored in detail. If the simulation only renders what's being observed, then what counts as observation? When you look at a rock, does the simulation need to render all the atoms in the rock, or just its surface appearance? When you cut the rock open, does it need to retroactively create an interior that's consistent with the exterior? What about bacteria on the rock? Are they conscious observers whose observations need to be rendered? Or are they just part of the background simulation? This leads to what Schwitzgebel calls the, quote, 13 in simulation theory. The simulation needs to decide, moment by moment, what to render in detail and what to leave as probabilistic blur. But making these decisions requires the simulation to predict what will be observed, which requires simulating the observer's decision-making processes, which requires simulating their brains in detail, which defeats the whole purpose of taking shortcuts. The simulation might need to be just as complex as a non-simulated universe, eliminating any computational advantage. There's also a more fundamental objection, raised by the philosopher David Papineau at King's College London. He argues that the simulation hypothesis rests on a category error, a confusion between the map and the territory. When we say the universe might be a simulation, we're imagining it as a computer program running on hardware in some base reality. But this assumes that the base reality has computers, hardware, physical substrates, things that exist in space and time. Yet space and time might themselves be features of the simulation, not features of the base reality. Think about it this way. When you play a video game, the game world has its own space and time. Characters in the game move through game space and experience game time. But the computer running the game exists in a different space and time, the real world's space and time. Now imagine you're a character in the game who figures out they're simulated. You might try to imagine the computer running you, but you'd inevitably imagine it as existing in some kind of space, taking up some volume, existing at some location. But the real computer exists in a completely different kind of space, one that's not part of your game world at all. Similarly, if our universe is a simulation, the hardware running it might not exist in anything we'd recognize as space or time. It might exist in some higher dimensional manifold, or in a realm where the concepts of space and time don't apply at all. The base reality might be so fundamentally different from our reality that we literally cannot conceive of it. Our brains evolved to navigate three-dimensional space and one-dimensional time. We might be constitutionally incapable of understanding what the base reality is like. This connects to a deeper philosophical problem known as the problem of induction. The philosopher David Hume pointed out in the 18th century that we can never be certain that the patterns we observe will continue into the future. Just because the sun has risen every day for billions of years doesn't logically guarantee it will rise tomorrow. We assume the laws of nature are constant, but this assumption itself cannot be proven. It's based on induction from past experience. The simulation hypothesis makes this problem worse. If we're in a simulation, the laws of physics might not be constant at all. The simulators could change them at any time. Gravity could suddenly stop working. The speed of light could double. Electrons could start repelling each other instead of attracting protons. We assume these things won't happen because they never have, but in a simulation, past behavior is no guarantee of future behavior. The programmers could patch the code at any moment. This leads to a kind of epistemological vertigo. If we're in a simulation, we can't trust anything. Our memories might be false. Our perceptions might be manipulated. The laws of physics might be temporary. Even our logical reasoning might be compromised. The simulators could be subtly altering our thought processes to prevent us from discovering the truth. We'd be like characters in a story who can never know they're in a story because the author controls their thoughts. The philosopher Hilary Putnam at Harvard University explored a related scenario in his famous brain in a vat thought experiment. Imagine your brain has been removed from your body and placed in a vat of nutrients. Electrodes stimulate your neurons to create the illusion of a normal life. You think you're reading this script, but actually, you're a disembodied brain being fed false sensory data. Now here's Putnam's insight. You can never prove you're not a brain in a vat, because any evidence you gather would itself be part of the illusion. The very concepts you use to think about the problem, quote 15, quote 16, quote 17, refer to things in your simulated experience, not to things in the external world. The simulation hypothesis is essentially a high-tech version of the brain in a vat scenario. And Putnam's conclusion applies here too. If you're in a simulation, you can never prove it from the inside, because all your evidence comes from within the simulation. You're trapped in a kind of epistemological prison, unable to access any information about the reality beyond your simulated experience. But wait. Some philosophers argue that this conclusion is too pessimistic. The philosopher Nick Bostrom himself has responded to these objections by pointing out that the simulation hypothesis does make some testable predictions. For instance, if we're in an ancestor simulation, we should expect to find ourselves living in a historically interesting period, a time of rapid technological change, major conflicts, significant discoveries. The simulators would be most interested in simulating pivotal moments in history, not boring stretches where nothing much happens. And indeed, we do find ourselves in an extraordinarily interesting time. We're living through the development of artificial intelligence, the exploration of space, the unraveling of the human genome, the discovery of exoplanets, the potential emergence of quantum computing. We're facing existential risks from climate change, nuclear weapons, and biotechnology. We're on the cusp of becoming a spacefaring civilization or destroying ourselves. If you were running an ancestor simulation, this is exactly the kind of period you'd want to simulate in detail. Of course, this reasoning has a selection bias problem. Every generation thinks it's living in uniquely important times. People in the Middle Ages thought they were living through the end times. People in the 19th century thought they were witnessing the pinnacle of human civilization. People in the 1960s thought they were experiencing a consciousness revolution. We might just be falling prey to the same bias, overestimating the significance of our own era because we're living through it. The physicist Max Tegmark has proposed a different kind of test. He suggests that if we're in a simulation, we might be able to detect it by looking for mathematical inconsistencies in the laws of physics. Real mathematics is perfectly consistent. There are no contradictions in the axioms of arithmetic or geometry. But a simulated universe might contain subtle mathematical errors, places where the programmers made mistakes or took shortcuts that create logical inconsistencies. Tegmark proposes searching for these inconsistencies by pushing physical theories to their limits, looking for places where different theories give contradictory predictions. For instance, quantum mechanics and general relativity are both extraordinarily successful theories, but they're mathematically incompatible. They can't both be exactly right. Most physicists assume this means we need a deeper theory, quantum gravity, that reconciles them. But what if the inconsistency is real? What if it's a bug in the simulation, a place where the programmers couldn't quite make the math work? This is a fascinating idea, but it has a problem. How do we distinguish between a bug in the simulation and a bug in our theories? When we find mathematical inconsistencies in physics, the natural assumption is that our theories are incomplete or incorrect, not that reality itself is inconsistent. We'd need some way to rule out all possible natural explanations before we could conclude that we'd found a genuine glitch in the simulation. And that might be impossible. There's also the question of what we'd do if we did find convincing evidence of simulation. The philosopher Preston Green's concern about simulation shutdown is real, but it's not the only worry. What if discovering we're in a simulation causes mass psychological trauma? What if people lose all sense of meaning and purpose, knowing that their lives are just code running on someone else's computer? What if society collapses because nobody sees the point of continuing? The psychologist Clay Routledge at North Dakota State University has studied how people respond to existential threats and meaning crises. His research suggests that humans are remarkably resilient. We find meaning even in absurd circumstances. We create purpose even when the universe seems indifferent. People in concentration camps found reasons to live. People facing terminal illness find joy in their remaining days. We might adapt to the knowledge that we're simulated just as we've adapted to other disturbing truths. That the Earth isn't the center of the universe, that humans evolved from apes, that consciousness emerges from meat. In fact, some philosophers argue that being in a simulation might actually make life more meaningful, not less. The philosopher David Chalmers points out that if we're in a simulation, then our existence has a purpose. We were created deliberately by the simulators for some reason. We're not cosmic accidents, random fluctuations in a meaningless void. We're intentional creations, designed beings, which gives our lives a kind of significance that they might lack in a purely natural universe. Moreover, if we're in a simulation, then the problem of suffering becomes more tractable. In a natural universe, suffering seems pointless, a byproduct of evolution, a consequence of entropy, a feature of reality that serves no purpose. But in a simulation, suffering might have a purpose. Maybe the simulators are testing how we respond to adversity. Maybe they're studying the emergence of compassion and cooperation under difficult conditions. Maybe our struggles are meaningful in ways we can't yet understand. This is starting to sound like theology, and that's not a coincidence. The simulation hypothesis has striking parallels to religious worldviews. The simulators are like gods, vastly more powerful than us, existing in a higher realm, creating and sustaining our reality. The base reality is like heaven, a perfect realm beyond our simulated world. The possibility of being uploaded to the base reality is like salvation. The fear of simulation shutdown is like the fear of divine judgment. The philosopher Philip Goff at Durham University has explored these parallels in detail. He argues that the simulation hypothesis is essentially a secular version of theism. It provides the same psychological benefits: a sense of cosmic purpose, the possibility of life after death, the hope that suffering has meaning, without requiring belief in the supernatural. It's religion for the scientifically minded, theology dressed up in the language of computer science. But this raises a troubling question. Are we taking the simulation hypothesis seriously because of the evidence, or because we want it to be true? Are we engaging in motivated reasoning, finding patterns where none exist because the alternative, that we're alone in an indifferent universe, is too bleak to accept? The history of science is full of examples of wishful thinking masquerading as rigorous inquiry. We need to be careful not to fall into the same trap. The physicist Lisa Randall at Harvard University has warned about this danger. She points out that the simulation hypothesis is attractive precisely because it's unfalsifiable. It can never be definitively disproven, which means believers can maintain their faith regardless of evidence. This is the hallmark of pseudoscience: theories that are immune to refutation, that can accommodate any observation, that survive not because they're true, but because they're flexible enough to avoid being proven false. Randall argues that we should focus on questions that can actually be answered through observation and experiment. Does space-time have a minimum length scale? Are the fundamental constants truly constant? Do quantum measurements reveal patterns in randomness? These are legitimate scientific questions with potentially testable answers. But the broader question of whether we're in a simulation might be forever beyond our reach, a metaphysical puzzle rather than a scientific problem. Yet even if the simulation hypothesis is unfalsifiable, it might still be useful. The philosopher of science Karl Popper argued that falsifiability is the criterion for distinguishing science from non-science. But he also acknowledged that unfalsifiable ideas can play important roles in scientific progress. They can inspire new research directions, suggest novel experiments, provide frameworks for organizing observations. The simulation hypothesis might be valuable not because it's true, but because it's productive. It generates interesting questions and pushes us to think about reality in new ways. Consider how the simulation hypothesis has already influenced physics. It's led researchers to investigate the computational limits of the universe, to search for quantization in space-time, to study information theory as a fundamental aspect of reality. These investigations are valuable, regardless of whether we're actually in a simulation. They're expanding our understanding of the relationship between information and physics, between computation and reality, between mathematics and nature. The physicist John Wheeler, who we mentioned earlier, believed that information is more fundamental than matter or energy. His quote, 18, concept suggests that physical reality emerges from information, that the universe is fundamentally made of bits of data rather than particles or fields. This idea has been enormously influential in modern physics, leading to developments in quantum information theory, black hole thermodynamics, and the holographic principle. And it was inspired, at least in part, by thinking about the universe as a kind of computation. Similarly, the physicist Seth Lloyd's work on the universe as a quantum computer has led to new insights about the limits of computation, the nature of complexity, and the arrow of time. Lloyd calculated that the universe has performed approximately 10 to the power of 120 operations since the Big Bang, processing about 10 to the power of 90 bits of information. These numbers are staggering, but they're finite. The universe has computational limits, which means it can only contain a finite amount of complexity, a finite number of distinguishable states. This has profound implications for questions about consciousness, free will, and the nature of time. If the universe is a computer with finite memory, then there are only so many possible configurations of matter and energy. Eventually, if the universe lasts long enough, it must repeat itself. You might live this exact life again, an infinite number of times, in an eternally recurring universe. This is the ancient idea of eternal recurrence, proposed by Nietzsche, but now grounded in information theory and computational physics. But we're getting ahead of ourselves. We're exploring implications of the simulation hypothesis without having established whether it's true. And that's the fundamental problem. We might never be able to establish it. We might be forever uncertain, living in a state of epistemological limbo, unable to prove or disprove that we're simulated. The philosopher Bertrand Russell illustrated this problem with his famous teapot analogy. He asked us to imagine claiming that there's a teapot orbiting the sun somewhere between Earth and Mars, too small to be detected by telescopes. This claim is unfalsifiable. We can't prove the teapot doesn't exist. But that doesn't mean we should take it seriously. The burden of proof lies with the person making the claim, and without evidence, we should reject it. Is the simulation hypothesis like Russell's teapot? An unfalsifiable claim that we should dismiss for lack of evidence? Or is it different because it's based on logical argument and probabilistic reasoning rather than arbitrary assertion? Bostrom's trilemma, that at least one of his three propositions must be true, seems more rigorous than claiming there's a teapot in space. But maybe that's an illusion. Maybe the trilemma rests on hidden assumptions that we haven't examined carefully enough. Let's look at those assumptions. Bostrom assumes that consciousness can be simulated, that you can create genuine subjective experience through computation. But what if consciousness requires something more than computation? What if it requires quantum effects in the brain, or some non-physical soul, or some property of matter that we haven't discovered yet? If consciousness can't be simulated, then ancestor simulations are impossible, and the entire argument collapses. The philosopher John Searle at Berkeley has argued for decades that computation alone cannot create consciousness. His famous Chinese room thought experiment suggests that following rules and manipulating symbols, which is all that computers do, cannot generate genuine understanding or subjective experience. A computer running a simulation of a brain might behave exactly like a conscious being, but it wouldn't actually be conscious. It would be a philosophical zombie, a being that acts conscious but has no inner experience. If Searle is right, then simulated beings wouldn't be conscious, which means they wouldn't count as observers in Bostrom's argument. The simulators might run billions of simulations, but those simulations would contain zero conscious beings, not billions. The ratio of simulated to real conscious beings would remain zero, and we'd have no reason to think we're simulated. But most philosophers and neuroscientists reject Searle's argument. They believe that consciousness is a physical process that emerges from the right kind of information processing. If you simulate a brain accurately enough, you simulate consciousness. The substrate doesn't matter, whether you're made of neurons or silicon or quantum fields. If you're processing information in the right way, you're conscious. This view, called functionalism, is the dominant position in philosophy of mind and cognitive science. If functionalism is correct, then Bostrom's argument stands. Simulated beings would be genuinely conscious, and the probability that we're simulated depends on how many simulations advanced civilizations run. But here's where another assumption comes in. Bostrom assumes that advanced civilizations would want to run ancestor simulations. But why would they? We run simulations for specific purposes: to predict weather, to design aircraft, to study disease spread, to train artificial intelligences. But we don't run simulations just for fun, especially not simulations that create conscious beings who might suffer. Creating conscious beings carries moral weight. It's not something to do casually. An advanced civilization might have ethical prohibitions against running ancestor simulations, especially if those simulations include suffering and death. The philosopher Thomas Metzinger has argued that creating conscious simulations might be morally wrong, analogous to creating sentient beings just to experiment on them. He suggests that advanced civilizations might recognize this and refrain from running such simulations, or at least limit them severely. If most advanced civilizations follow this ethical principle, then the number of simulations would be much smaller than Bostrom assumes, and the probability that we're simulated would drop accordingly. There's also the question of whether advanced civilizations would survive long enough to run simulations. The physicist Enrico Fermi famously asked, "If intelligent life is common in the universe, where is everybody? Why haven't we detected any signs of alien civilizations?" One possible answer is the Great Filter, some challenge that civilizations typically fail to overcome, causing them to go extinct before they can colonize the galaxy or run sophisticated simulations. Maybe the Great Filter is nuclear war. Maybe it's climate change. Maybe it's artificial intelligence that turns hostile. Maybe it's something we haven't even thought of yet. If the Great Filter lies ahead of us, then very few civilizations reach the point where they can run ancestor simulations. And if very few civilizations run simulations, then the probability that we're in one drops dramatically. Alternatively, maybe the great filter is behind us. Maybe the hard step is the origin of life, or the evolution of complex cells, or the development of intelligence. Maybe we're one of the rare civilizations that made it this far, and our future is relatively secure. In that case, we might eventually run ancestor simulations ourselves, and the simulation hypothesis becomes more plausible. But notice what we're doing here. We're piling assumption upon assumption, each one uncertain, each one affecting the final probability calculation. The simulation hypothesis isn't a simple claim with a clear probability. It's a complex web of assumptions about consciousness, computation, the future of civilization, the ethics of advanced beings, and the nature of reality itself. Change any one of these assumptions, and the conclusion changes. This is why many physicists remain skeptical. The simulation hypothesis isn't a single testable theory. It's a family of related ideas, each with different implications and different probabilities. Some versions are more plausible than others. Some make testable predictions, others don't. Some are compatible with known physics, others require speculative assumptions. We can't simply say there's a 50% chance we're in a simulation, without specifying exactly which version of the hypothesis we're talking about. Moreover, even if we accept Bostrom's logic, the 50% figure is misleading. Bostrom himself has clarified that he's not claiming there's a 50% probability we're simulated. He's claiming that at least one of his three propositions must be true, and if the first two are false, then the third must be true. But we don't know the probabilities of the first two propositions. Maybe there's a 90% chance that civilizations destroy themselves before running simulations. In that case, the probability that we're simulated would be much lower than 50%. The philosopher David Chalmers has attempted to calculate more precise probabilities by assigning likelihoods to each of Bostrom's propositions. He estimates that there's perhaps a 25% chance that civilizations typically go extinct before running simulations, a 25% chance that they lose interest in running them, and a 50% chance that they do run them. If they run them, and if we assume they run many simulations, then the probability that we're in a simulation might be around 40%. But Chalmers emphasizes that these numbers are highly speculative, based on guesses about unknowable future events. Other philosophers have arrived at different numbers. Some estimate the probability as low as 1%, others as high as 99%. The range of estimates reflects our deep uncertainty about the underlying assumptions. We simply don't know enough about the future of civilization, the nature of consciousness, or the ethics of advanced beings to make confident probability judgments. And this brings us back to the fundamental question: is the simulation hypothesis science or philosophy? Can it be tested, or is it forever beyond empirical investigation? The answer might be, it depends. Some versions of the hypothesis make testable predictions. Others don't. Some can be investigated through physics experiments. Others require philosophical analysis. The simulation hypothesis sits at the boundary between science and philosophy, between the empirical and the metaphysical, between what we can know and what we can only speculate about. Perhaps that's where it should stay. Perhaps the value of the simulation hypothesis isn't in answering the question definitively, but in forcing us to think carefully about the nature of reality, the limits of knowledge, and the relationship between mind and matter. It's a thought experiment that reveals our assumptions, challenges our intuitions, and expands our conception of what's possible. The physicist Niels Bohr once said that the purpose of philosophy is not to provide answers, but to deepen the questions. The simulation hypothesis does exactly that. It takes the ancient question, what is real, and gives it new depth, new urgency, new scientific relevance. It forces us to confront the possibility that reality might be radically different from what we assume, that our most basic beliefs about existence might be wrong, that we might be living in a kind of cosmic illusion. But even if we can never know for certain whether we're in a simulation, the question itself is valuable. It pushes us to develop new physics, new mathematics, new ways of thinking about information and computation. It inspires experiments that probe the fundamental structure of space-time. It generates philosophical insights about consciousness, reality, and knowledge. Whether or not we're actually in a simulation, thinking about the possibility makes us better scientists and deeper thinkers. And maybe that's the point. Maybe the simulation hypothesis is less like a scientific theory to be proven or disproven, and more like a lens through which to view reality, a perspective that reveals aspects of existence we might otherwise miss. It's a way of taking seriously the idea that information is fundamental, that computation is ubiquitous, that reality might be stranger than we ever imagined. In the end, we're left with uncertainty. We have suggestive evidence, but no proof. We have logical arguments, but no definitive conclusions. We have probabilities that depend on unknowable assumptions. We're in a state of epistemological suspension, unable to confirm or deny that we're living in a simulation, forced to live with ambiguity and doubt. But perhaps that's the human condition anyway. We've always lived with uncertainty about the ultimate nature of reality. We've always had to make decisions and find meaning without knowing for sure what's real and what's illusion. The simulation hypothesis just makes this uncertainty explicit, brings it to the surface, forces us to acknowledge what we've always known deep down, that we might be wrong about everything, that reality might be fundamentally different from what we perceive, that we're navigating existence with incomplete information and imperfect understanding. And yet, we persist. We build lives, form relationships, pursue goals, create meaning. We do this not because we're certain about the nature of reality, but despite our uncertainty. We do it because we're human, because we're conscious beings who experience joy and suffering, love and loss, hope and despair. Whether we're made of atoms or bits, whether we're in a simulation or a base reality, these experiences are real to us. They matter to us. They constitute our existence. So maybe the question isn't whether we're in a simulation. Maybe the question is, what do we do with the possibility? How does it change how we live? How does it affect our values, our choices, our sense of purpose? These are the questions we need to explore next. The practical implications of living in a world where we might be simulated, where reality might be code, where consciousness might be computation. So here we are, suspended between certainty and doubt, between the real and the simulated, between what we can know and what we can only wonder about. But now we need to confront something that makes this entire discussion not just intellectually fascinating, but existentially urgent. Because if there's even a chance, even a small probability, that we're living in a simulation, then everything changes. Not just our understanding of physics or philosophy, but how we should live, what we should value, what we should do with the brief span of consciousness we've been granted. Let's start with the most immediate question. If we discovered tomorrow, with absolute certainty, that we're in a simulation, should you get out of bed? Should you go to work? Should you continue pursuing your goals, maintaining your relationships, caring about your future? Or would it all become meaningless? A cosmic joke, a pointless exercise in following scripts written by programmers you'll never meet. The philosopher David Chalmers argues that the answer is unequivocally yes, you should get out of bed. Reality, he insists, is not about the substrate. It's about the structure, the patterns, the relationships. The love you feel for your family is real because it's a genuine pattern of information processing in your brain, regardless of whether that brain is made of neurons or code. The beauty of a sunset is real because it's a genuine perceptual experience, regardless of whether the photons are simulated or natural. Your achievements matter because they're genuine accomplishments within the framework of your existence, regardless of what that framework is running on. But is this really satisfying? Imagine you're playing a video game, and you spend hundreds of hours building a virtual empire, forming alliances, achieving victories. Then someone tells you, "You know this is just a game, right? None of it is real. You're just manipulating pixels on a screen." Would you feel the same sense of accomplishment? would your victories still matter? Most people would say no. There's something about knowing it's a game that diminishes the significance. We care about real-world achievements precisely because they're real, because they have consequences beyond the game, because they connect to something larger than ourselves. If our entire universe is a game, then what are we connecting to? What larger context gives our actions meaning? The philosopher Thomas Nagel at New York University has explored this problem in his work on the absurd. He argues that human life is inherently absurd because we take ourselves seriously. We pursue goals, make plans, care deeply about outcomes, while simultaneously being aware that from a cosmic perspective, none of it matters. We're tiny specks on a small planet orbiting an average star in an unremarkable galaxy, and everything we do will eventually be forgotten. The simulation hypothesis amplifies this absurdity. Not only are we cosmically insignificant, we might not even be cosmically real. Yet Nagel's conclusion is surprisingly optimistic. He argues that recognizing the absurdity of existence doesn't require us to stop caring. Instead, it frees us. If nothing ultimately matters, then we're free to create our own meaning, to decide what's important, to live according to our own values rather than some cosmic script. The simulation hypothesis, in this view, is liberating rather than depressing. It removes the burden of cosmic significance and gives us permission to simply be human. But there's a darker possibility we need to consider. What if the simulators are watching? What if they're judging us, evaluating our choices, deciding which simulated beings are worth preserving and which can be deleted? This transforms the simulation hypothesis from a metaphysical curiosity into a moral imperative. How you live might literally determine whether you continue to exist. The transhumanist philosopher Nick Bostrom has suggested that if we're in an ancestor simulation, we should try to be historically interesting. The simulators are presumably running the simulation to study pivotal moments in history, to understand how civilizations develop and make crucial decisions. If you want to ensure your continued existence, you should try to be significant, memorable, worthy of detailed simulation. Be a leader, an innovator, a revolutionary. Make history. Leave a mark. But this advice is troubling for several reasons. First, it's elitist. Most people can't be historically significant. Most lives are ordinary, filled with small joys and quiet struggles that don't make it into history books. Are these lives less worthy of simulation? Should ordinary people worry that they'll be deleted as irrelevant background characters? Second, it's morally questionable. Some of the most historically significant people have been monsters, tyrants, mass murderers, architects of genocide. If the goal is to be interesting to the simulators, should we pursue significance at any cost, even if it means causing suffering? This can't be right. Any ethical framework that encourages evil for the sake of being memorable is fundamentally broken. Third, it assumes the simulators think like us, value what we value, find interesting what we find interesting. But if they're vastly more advanced than us, or if they're artificial intelligences, or if they're alien beings with completely different psychology, they might have utterly different criteria for what's worth preserving. They might value kindness over achievement, or creativity over power, or something we can't even conceive of. Trying to please them might be like an ant trying to please a human. The ant has no idea what the human wants, and its efforts are likely to be completely misguided. So perhaps we should abandon the idea of living for the simulators and instead focus on living for ourselves and each other. This is the approach advocated by the philosopher Susan Schneider at Florida Atlantic University. She argues that even if we're in a simulation, we're still conscious beings with genuine experiences, genuine relationships, genuine capacity for joy and suffering. Our moral obligations to each other don't disappear just because we're simulated. If anything, they become more important because we're all we have, fellow travelers in a potentially artificial universe, creating meaning together in the face of cosmic uncertainty. This perspective suggests that the simulation hypothesis shouldn't change how we live at all. We should still pursue happiness, cultivate relationships, reduce suffering, seek truth, create beauty. These values don't depend on whether we're in a base reality or a simulation. They emerge from our nature as conscious, social beings who care about our experiences and the experiences of others. But there's a complication. If we're in a simulation, then our values themselves might be programmed. The things we care about, love, justice, beauty, truth, might not be universal goods. They might be arbitrary preferences installed by the simulators to make the simulation run smoothly or to test certain hypotheses. We might be like characters in a story who think they're making free choices, but are actually following a script written by an author with specific narrative goals. The philosopher Galen Strawson at the University of Texas has argued that this kind of manipulation doesn't undermine moral responsibility. Even if your values are programmed, they're still your values. You still experience them as genuine preferences, still make choices based on them, still feel satisfaction when you act according to them. The origin of your values doesn't determine their validity. What matters is that they're yours, that they guide your actions, that they give your life structure and purpose. But this seems too easy. Imagine you discovered that your love for your spouse was programmed into you by the simulators as part of an experiment on pair bonding. Would you still feel the same way about your relationship? Or would you feel manipulated, violated, robbed of authentic emotion? Most people would feel betrayed. We want our deepest feelings to be genuinely ours, not imposed from outside. Yet here's the paradox. Even in a non-simulated universe, your emotions are programmed by evolution and shaped by your environment. Your capacity for love emerged through millions of years of natural selection because it helped your ancestors survive and reproduce. Your specific feelings for your spouse developed through a complex interaction of genetics, neurobiology, personal history, and social conditioning. In what sense are these feelings more authentic than feelings that might be programmed by simulators? The philosopher Daniel Dennett at Tufts University has spent decades arguing that free will is compatible with determinism. Even if your choices are determined by prior causes, whether those causes are physical laws or simulation code, you can still be free in the sense that matters. You're free if your choices flow from your own desires, beliefs, and values, if you're not being coerced or constrained by external forces. The simulation hypothesis doesn't threaten this kind of freedom. You're still making choices based on your own mental states, even if those mental states are implemented in code rather than neurons. But there's a more insidious threat to freedom that the simulation hypothesis raises. What if the simulators are actively intervening in your life, subtly manipulating events to steer you in certain directions? What if that job opportunity that seemed like lucky timing was actually the simulators adjusting probabilities? What if that chance encounter that changed your life was actually a scripted event? What if your sense of agency is an illusion and you're actually being puppeted through a predetermined narrative? This is where the simulation hypothesis starts to feel less like an interesting philosophical puzzle and more like a paranoid nightmare. If the simulators can intervene at will, then you have no way to distinguish between your own choices and their manipulations. Every decision you make might be influenced by invisible hands. Every outcome might be rigged. You'd be living in a kind of cosmic Truman Show where everything is staged and everyone is an actor except you. Except you might be an actor too, reading lines you think you're improvising. The philosopher Eddie Namias at Georgia State University has studied how people respond to scenarios involving determinism and manipulation. His research shows that people are much more troubled by manipulation than by determinism. We can accept that our choices are determined by prior causes, but we can't accept that someone is pulling our strings, making us dance like puppets. Manipulation threatens our sense of self in a way that mere determinism doesn't. If we're in a simulation with active intervention by the simulators, then we're being manipulated on a cosmic scale. And this raises a profound question. Are we morally responsible for our actions if we're being manipulated? If the simulators are steering events, if they're influencing our thoughts and choices, then can we be blamed for our mistakes or praised for our achievements? The legal philosopher Stephen Morse at the University of Pennsylvania has argued that responsibility requires a certain kind of control over our actions. We're responsible for what we do if we could have done otherwise, if our choices flow from our own rational deliberation, if we're not being coerced or deceived. But in a simulation with active intervention, these conditions might not be met. We might think we're deliberating freely, but actually, we're being guided by the simulators. We might think we could have done otherwise, but actually, the outcome was predetermined by the simulation's code. This has disturbing implications for justice. If we're not truly responsible for our actions, then punishment becomes unjust. We can't blame people for crimes they were programmed to commit. We can't praise people for achievements they were manipulated into accomplishing. The entire framework of moral evaluation collapses. We're left in a world where actions happen, but nobody is truly responsible for them. Yet most philosophers reject this conclusion. They argue that even in a deterministic or simulated universe, we can still make meaningful distinctions between free and coerced actions, between rational and irrational choices, between praiseworthy and blameworthy behavior. What matters is not whether your actions are determined, but how they're determined. If they flow from your own values and reasoning, you're responsible. If they're imposed by external force or manipulation, you're not. But this distinction becomes blurry in a simulation. Where do you draw the line between your own values and the simulator's programming? If the simulators installed your values, are they really yours? If they subtly influence your reasoning, are your conclusions really your own? The boundary between self and simulation becomes porous, uncertain, impossible to locate precisely. Perhaps we need to accept that in a simulated universe, the concept of individual autonomy needs to be revised. We're not isolated agents making independent choices. We're nodes in a network, parts of a larger system, expressions of a computational process that includes both our own mental states and the simulation's underlying code. Our choices are real, but they're not separate from the simulation. They're part of it, emergent from it, inseparable from it. This view aligns with Buddhist philosophy, which has long argued that the self is an illusion. There is no separate, independent, quote, 24, making choices. There's just a flow of experiences, a stream of consciousness, a process of becoming. The simulation hypothesis, in this interpretation, is just a modern way of expressing an ancient insight, that we're not what we think we are, that our sense of separate selfhood is a convenient fiction, that reality is more interconnected and less individuated than our everyday experience suggests. But even if we accept this dissolution of the self, we still face practical questions about how to live. Should we try to escape the simulation? Should we try to contact the simulators? Should we try to hack the code and gain control over our own reality? These questions aren't just philosophical. They're becoming technologically relevant as we develop our own simulation capabilities and artificial intelligence. The computer scientist Rizwan Virk at Arizona State University has proposed that if we're in a simulation, we might be able to find exploits, bugs in the code that allow us to do things that shouldn't be possible. In video games, players constantly search for glitches that give them advantages, ways to walk through walls, duplicate items, access hidden areas. Could we do something similar in our universe? Could we find loopholes in the laws of physics that allow us to manipulate reality in ways the simulators didn't intend? Some physicists think this might already be happening. Quantum mechanics allows for phenomena that seem to violate classical logic. Particles that exist in multiple states simultaneously. Effects that propagate faster than light. Measurements that retroactively determine past events. These phenomena are well established experimentally, but they're deeply weird. They don't make intuitive sense. They feel like glitches, like places where the simulation's code breaks down or behaves unexpectedly. What if we could exploit these quantum glitches? What if we could use quantum entanglement to send information faster than light, or use quantum superposition to perform impossible computations, or use quantum measurement to retroactively change the past? These capabilities would give us a kind of power over reality that seems almost magical. We'd be like players who've discovered cheat codes, able to bend the rules of the game to our advantage. But there's a danger here. If we start exploiting glitches in the simulation, the simulators might notice. They might patch the bugs, closing the loopholes we've discovered. Or worse, they might decide the simulation has become corrupted and shut it down entirely. This is Preston Green's simulation shutdown problem again. The more we investigate the nature of our reality, the more we risk triggering our own deletion. Yet, we can't simply stop investigating. Scientific curiosity is fundamental to human nature. We're driven to understand, to explore, to push boundaries. Telling scientists not to investigate the simulation hypothesis is like telling them not to breathe. It goes against everything that makes us human. We have to pursue truth, even if it's dangerous, even if it might lead to our own destruction. The physicist Martin Rees at Cambridge University has written extensively about existential risks, threats that could destroy humanity or permanently curtail our potential. He lists nuclear war, climate change, biotechnology, and artificial intelligence as major risks. But he also mentions more speculative possibilities. Physics experiments that could destroy the universe, nanotechnology that could consume the biosphere, and yes, discovering we're in a simulation and triggering a shutdown. Rees argues that we need to be cautious about pursuing certain kinds of knowledge. Not all truths are safe to know. Some discoveries might be so dangerous that we're better off remaining ignorant. This is a controversial position. It goes against the scientific ethos of pursuing truth wherever it leads. But Rees insists that survival must take precedence over curiosity. If investigating the simulation hypothesis poses an existential risk, we should proceed very carefully, if at all. But how do we balance caution with curiosity? How do we decide which investigations are too dangerous to pursue? The problem is that we can't know in advance which discoveries will be dangerous. The simulators might not care if we discover we're simulated. They might even want us to discover it. Or they might have completely different concerns that we can't anticipate. We're trying to second-guess beings who might be incomprehensibly more advanced than us. It's an impossible task. Perhaps the solution is to proceed with investigation, but also with humility. We should search for evidence of simulation, but we should also acknowledge the limits of our understanding. We should develop theories and run experiments, but we should also recognize that we might be wrong, that reality might be stranger than any of our theories can capture, that we're operating with incomplete information and imperfect tools. This brings us to one of the most important implications of the simulation hypothesis. It forces us to confront the limits of human knowledge. For centuries, we've been expanding our understanding of the universe, pushing back the boundaries of ignorance, explaining more and more of reality through science and mathematics. We've been remarkably successful. We've split the atom, decoded the genome, detected gravitational waves, photographed black holes. We've come to believe that given enough time and resources, we can understand anything. But the simulation hypothesis suggests there might be fundamental limits to what we can know. If we're in a simulation, there are questions we can never answer from the inside. We can never know the true nature of the base reality. We can never fully understand the simulator's motivations. We can never be certain whether what we observe is genuine or manipulated. We're like characters in a novel trying to understand the author. We can make guesses, but we can never step outside the text to verify them. The physicist David Deutsch at Oxford has argued that there are no fundamental limits to knowledge. Any question that can be asked can, in principle, be answered through the right combination of theory and experiment. But the simulation hypothesis challenges this optimism. It suggests that some questions might be forever beyond our reach. Not because we lack the intelligence or technology to answer them, but because we lack access to the necessary information. We're trapped inside the simulation, and the information we need is outside, in the base reality we can never observe. This is a humbling realization. It means that no matter how advanced we become, no matter how sophisticated our theories or powerful our instruments, there will always be aspects of reality we cannot access, questions we cannot answer, truths we cannot verify. we're fundamentally limited by our position inside the simulation, by our inability to step outside and see the larger context. Yet this limitation might not be unique to simulated universes. Even in a base reality, there might be fundamental limits to knowledge. The physicist Werner Heisenberg showed that we cannot simultaneously know both the position and momentum of a particle with perfect precision. The mathematician Kurt Gödel proved that any sufficiently complex logical system contains true statements that cannot be proven within that system. The cosmologist Stephen Hawking argued that information that falls into a black hole is lost forever, creating a fundamental limit on what we can know about the universe's history. So perhaps the simulation hypothesis doesn't introduce new limits to knowledge. It just makes existing limits more explicit and more troubling. It forces us to acknowledge that we're not omniscient, that we never will be, that there are aspects of reality that will forever remain mysterious. And maybe that's okay. Maybe the pursuit of knowledge is valuable not because we'll eventually know everything, but because the pursuit itself is meaningful, because it expands our understanding even if it never reaches completion, because it's part of what makes us human. The philosopher Karl Popper argued that science progresses not by proving theories true, but by proving them false. We can never be certain that a theory is correct, but we can be certain when it's wrong. Science advances through a process of conjecture and refutation, proposing bold hypotheses and then testing them rigorously, discarding those that fail and refining those that survive. This process never ends. There's no final theory, no ultimate truth, just an endless cycle of better and better approximations. The simulation hypothesis fits perfectly into this framework. We can't prove we're in a simulation, but we can look for evidence that would falsify the hypothesis. We can make predictions and test them. We can refine our theories based on what we observe. We can gradually narrow down the possibilities, even if we never reach absolute certainty. This is how science works. This is how we make progress in understanding reality, simulated or otherwise. And here's what's remarkable. Even if we can never prove we're in a simulation, the investigation itself is valuable. It's pushing us to develop new physics, new mathematics, new ways of thinking about information and computation. It's forcing us to question our assumptions about reality, consciousness, and existence. It's expanding our conception of what's possible, what's knowable, what's real. The physicist John Wheeler, in his final years, became increasingly convinced that reality is participatory, that observers play a fundamental role in bringing the universe into existence. He proposed that the universe is a self-excited circuit, where the present creates the past through the act of observation. This sounds mystical, but it's grounded in quantum mechanics, in the way that measurements collapse wave functions and determine outcomes. If Wheeler is right, then we're not passive observers of reality. We're active participants in creating it. The simulation hypothesis adds another layer to this idea. If we're in a simulation, then our observations might literally be creating reality, not just collapsing quantum wave functions, but actually causing the simulation to render details that didn't exist before. We'd be co-creators of our universe, working in partnership with the simulators, bringing reality into existence through the act of looking, measuring, investigating. This is a profound shift in perspective. It means that science isn't just about discovering pre-existing truths, it's about participating in the creation of reality. Every experiment we run, every measurement we make, every observation we record is helping to determine what's real, what exists, what the universe is. We're not just studying the simulation, we're shaping it, influencing it, making it what it is through our engagement with it. And if this is true, then the question of whether we're in a simulation becomes less important than the question of what we do with our reality, however it's implemented. We have agency. We have influence. We have the power to shape our world through our choices, our actions, our investigations. Whether we're made of atoms or bits, whether we're in a base reality or a simulation, we're participants in the grand project of existence, contributors to the ongoing creation of reality. This brings us full circle to where we started. the question of how to live in a potentially simulated universe. And the answer, perhaps, is this. We live authentically, courageously, curiously. We pursue truth even when it's uncomfortable. We create meaning even when the universe seems indifferent. We love each other even when we're uncertain about the nature of reality. We build, we explore, we question, we wonder. Because in the end, whether we're in a simulation or not, we're conscious beings having genuine experiences. We feel joy and pain. We form connections with others. We create art and science and philosophy. We struggle with questions of meaning and purpose. We face our mortality with courage or fear or acceptance. These experiences are real, regardless of the substrate they're running on. They matter, regardless of whether they're implemented in neurons or code. The simulation hypothesis doesn't diminish the value of human experience. It amplifies it. It shows us that consciousness, that subjective experience, that inner life we all possess is so fundamental, so important, that it can exist independent of any particular physical implementation. You're not your body. You're not your brain. You're the pattern, the process, the flow of information that constitutes your consciousness. And that pattern is real, is valuable, is worthy of respect and protection, whether it's running on biological hardware or computational substrate. So yes, get out of bed, go to work, pursue your goals, love your family, create beauty, seek truth, reduce suffering. These imperatives don't depend on whether you're in a simulation. They emerge from your nature as a conscious being, from your capacity to experience and to care, from your connection to other conscious beings who share this strange existence with you. And if we are in a simulation, if we discover tomorrow that everything we thought was real is actually code running on some unimaginable computer in a base reality we can never access, then we adapt. We adjust our understanding. We incorporate this new knowledge into our worldview. But we don't stop living. We don't stop caring. We don't stop being human, because that's what we are, ultimately. We're human. We're conscious. We're alive. And whether we're made of atoms or algorithms, whether we're in a base reality or nested simulations a million layers deep, these facts remain true. We exist. We experience. We matter. The simulation hypothesis isn't a threat to human dignity or meaning. It's a reminder that consciousness is more fundamental than matter, that experience is more real than substrate, that what we are transcends the question of how we're implemented. We're not just biological machines or computational processes. We're subjects of experience, centers of awareness, beings who feel and think and care. And in a universe that might be simulated, that might be code, that might be nothing more than information processing in some vast computer, consciousness stands out as the one thing that's undeniably real. You can doubt whether the external world exists. You can question whether other people are conscious. You can wonder whether you're in a simulation. But you cannot doubt your own consciousness. You cannot question your own experience. Descartes was right. I think, therefore I am. Your consciousness is the one certainty, the one rock-solid foundation on which everything else rests. So perhaps the simulation hypothesis, rather than undermining reality, actually reveals what's most real. Not matter, not energy, not space or time, but consciousness itself, experience itself, the subjective inner life that each of us possesses and that constitutes our existence. This is what's real. This is what matters. This is what we should protect and cherish and celebrate. Whether we're in a simulation or not, we're conscious beings navigating existence together, creating meaning in the face of uncertainty, building lives worth living despite our ignorance about ultimate reality. And that's enough. That's more than enough. That's everything. But now we need to step back and confront something even more profound than whether we're in a simulation. We need to ask, what does it mean that we can even ask this question? What does it reveal about the nature of consciousness, of reality, of existence itself, that beings like us, whether made of atoms or algorithms, can contemplate our own possible artificiality? Think about what's happening right now, in this moment. You're processing information, words, ideas, concepts, and somehow, mysteriously, these patterns of information are giving rise to subjective experience. You're not just computing, you're experiencing. You're aware. There's something it's like to be you, reading these words, contemplating these ideas. And this fact, this undeniable reality of consciousness, is perhaps more mysterious than any simulation hypothesis. The philosopher David Chalmers calls this the, quote, 26 we can explain, in principle, how the brain processes information, how neurons fire, how signals propagate through neural networks. But we cannot explain why this information processing gives rise to subjective experience. Why does it feel like something to be you? Why is there an inner life, a first-person perspective, a stream of consciousness? The simulation hypothesis doesn't solve this problem, it just relocates it. Whether you're implemented in neurons or code, the mystery of consciousness remains. And here's what makes this mystery so profound. Consciousness might be the only thing in the universe that's directly, immediately, undeniably real. Everything else, matter, energy, space, time, other people, the external world, you know only through your conscious experience. You infer their existence from sensory data, from patterns in your perceptions. But consciousness itself requires no inference. It's self-evident. It's the one thing you cannot doubt, because doubting requires consciousness. Descartes understood this 400 years ago, and the simulation hypothesis only makes his insight more relevant. So perhaps we've been asking the wrong question all along. Perhaps the question isn't, quote, 27, but rather, quote, 28. Because if consciousness is fundamental, if it's not just an emergent property of complex computation, but something more basic, more essential, then the distinction between simulated and real might dissolve entirely. The physicist Max Tegmark has proposed what he calls the mathematical universe hypothesis, that reality is literally made of mathematics, that physical existence is just mathematical structure. In this view, there's no difference between a underscore quote underscore 29 underscore universe and a underscore quote underscore 30 underscore 1, because both are mathematical structures. The only question is whether one mathematical structure is embedded within another. But they're equally real, equally existent, equally valid as universes. If Tegmark is right, then consciousness might be what it feels like to be a certain kind of mathematical structure, a structure complex enough to model itself, to represent its own states, to have recursive self-awareness. You're not in a simulation or in a base reality. You're a pattern of information that has become aware of itself, a mathematical structure that has achieved consciousness. And this is true regardless of what substrate implements you. This perspective offers a strange kind of liberation. It means that the question of simulation becomes almost irrelevant. What matters is not whether you're real, but that you're conscious, that you experience, that you're a subject of awareness navigating existence. The substrate is just implementation details. The reality is the pattern, the structure, the consciousness itself. But we still don't know what consciousness is. We don't know why certain patterns of information processing give rise to subjective experience while others don't. We don't know if consciousness requires biological neurons or if it can exist in silicon, in quantum computers, in the mathematical structures that Tegmark describes. We don't know if consciousness is continuous or discrete, unified or distributed, fundamental or emergent. And here's what's truly humbling. We might never know. The nature of consciousness might be one of those questions that's forever beyond our reach, not because we lack intelligence or technology, but because consciousness cannot fully understand itself. It's like trying to see your own eyes without a mirror, or trying to bite your own teeth. There's a fundamental limitation built into the structure of the problem. The philosopher Thomas Nagel explored this in his famous paper, quote, 32. He argued that we can never truly understand what it's like to be a bat, because consciousness is inherently subjective. We can study bat brains, map their neural circuits, understand their echolocation systems, but we can never experience what it's like to perceive the world through echolocation, to have a bat's sensory apparatus, to be a bat. There's an explanatory gap between objective description and subjective experience that might be unbridgeable. If we can't understand bat consciousness, how can we understand our own? How can we know if artificial intelligences are conscious? How can we determine if simulated beings have genuine subjective experience? We're trapped inside our own consciousness, unable to directly access anyone else's, unable to verify whether the patterns of behavior we observe in others correspond to genuine inner experience or are just sophisticated mimicry. This is the problem of other minds, and the simulation hypothesis makes it worse. In a simulated universe, you might be the only conscious being. Everyone else might be philosophical zombies, beings that behave exactly like conscious entities but have no inner experience. The simulators might have given you consciousness, but saved computational resources by making everyone else unconscious automatons. You'd have no way to tell. The people you love, the relationships you cherish, might be one-sided, you experiencing genuine emotion toward beings who feel nothing at all. This is a disturbing thought, but it's also unfalsifiable. You can never prove that other people are conscious. You can only infer it from their behavior, from the fact that they're similar to you, from the principle that the simplest explanation is usually correct. But in a simulation, simplicity might not apply. The simulators might have reasons to create a universe with only one conscious being. Maybe consciousness is expensive to simulate. Maybe they're studying your reactions to a world of unconscious actors. Maybe you're the experiment, and everyone else is just part of the apparatus. But here's the thing. You have to live as if other people are conscious. You have to treat them as subjects of experience, as beings who matter, as entities worthy of moral consideration. Because if you're wrong, if they are conscious and you treat them as mere objects, you're committing a profound moral error. The stakes are too high to gamble on solipsism. You must assume consciousness in others, even if you can never prove it. This is what the philosopher John Rawls called the veil of ignorance. When making moral decisions, you should imagine that you don't know which person you'll be. You might be anyone in the situation. This forces you to consider everyone's interests equally, because you might end up being any of them. In a potentially simulated universe, the veil of ignorance becomes even more important. You don't know who's conscious and who isn't. You don't know if you're the only real being or one of billions. So you must treat everyone as if they're conscious, as if they matter, as if their experiences are as real as yours. And this brings us to perhaps the most important implication of the simulation hypothesis. It doesn't change our moral obligations. Whether we're in a simulation or not, whether other people are genuinely conscious or sophisticated zombies, we should still act with compassion, with kindness, with respect for the apparent experiences of others. Because the alternative, treating people as mere objects, as disposable NPCs in a cosmic video game, is morally monstrous. The philosopher Peter Singer has argued that the capacity to suffer is what gives beings moral status. If something can experience pain, if it can feel distress, if it has interests that can be frustrated, then we have obligations toward it. This principle applies regardless of substrate. A simulated being that experiences suffering has the same moral status as a biological being that experiences suffering. The implementation doesn't matter. The experience does. So if we're in a simulation, and if other simulated beings are conscious, then we have the same moral obligations toward them that we'd have in a base reality. We should reduce suffering. We should promote well-being. We should respect autonomy. We should create conditions for flourishing. The simulation hypothesis doesn't give us permission to treat existence as a game where nothing matters. It reminds us that consciousness matters, that experience matters, that suffering is real regardless of the substrate it's implemented on. But there's still something we haven't addressed, something that makes the simulation hypothesis not just philosophically interesting, but existentially urgent. We're not just passive observers wondering if we're simulated. We're on the verge of creating our own simulations. Within decades, perhaps within years, we'll have the technology to create artificial intelligences that might be conscious, to run simulations that might contain sentient beings, to become simulators ourselves. And this raises a profound moral question. Should we? If creating conscious simulations means creating beings who can suffer, who can experience fear and pain and loss, do we have the right to do it? Are we prepared to take responsibility for the well-being of the conscious beings we create? Or would creating such simulations be a form of cosmic cruelty, bringing sentient beings into existence just to satisfy our curiosity or serve our purposes? The philosopher Thomas Metzinger has argued that we should be extremely cautious about creating artificial consciousness. He calls it the most important ethical issue of our time. If we create conscious AIs, we become responsible for their welfare. We become, in effect, gods to these beings, creators who determine the conditions of their existence. And history shows that gods are often cruel, indifferent, or absent. We need to be better than that. But there's another possibility, one that's more hopeful. Maybe the simulators, if they exist, are watching to see what we do when we gain the power to create simulations ourselves. Maybe this is a test, a rite of passage, a threshold that civilizations must cross. How we treat the conscious beings we create might determine how the simulators treat us. If we're compassionate, responsible, ethical creators, maybe they'll be the same. If we're cruel or indifferent, maybe that's what we deserve in return. This is speculation, of course. We have no evidence that the simulators care about our moral development, or that they're judging us by any criteria we'd recognize. But it's a useful thought experiment. It forces us to think carefully about the ethics of creation, about our responsibilities as potential simulators, about the kind of gods we want to be. And here's what's remarkable. We're already creating simulations. Not simulations of conscious beings, not yet, but simulations of physical systems, of biological processes, of social dynamics. We simulate weather patterns to predict hurricanes. We simulate protein folding to design drugs. We simulate economies to test policies. We simulate galaxies to understand cosmic evolution. We're becoming simulators, gradually, incrementally, learning how to create artificial realities that mirror aspects of our own. As these simulations become more sophisticated, as we add more detail and complexity, we'll eventually face the question: have we created consciousness? At what point does a simulation become sophisticated enough that the beings within it are genuinely aware, genuinely experiencing, genuinely deserving of moral consideration? We don't know where that threshold is. We might cross it without realizing it. We might already have crossed it. This is the problem that the philosopher Nick Bostrom calls, quote, 35. If we create simulations that contain conscious beings, we're morally responsible for those beings, but we might not know if they're conscious. We might create suffering without intending to, without even realizing we've done it. This is a profound moral risk, one that we need to take seriously as we develop more advanced AI and simulation technologies. But there's also an opportunity here. If we're thoughtful, careful, ethical in how we create simulations, we might be able to create universes that are better than our own. We could create simulations without suffering, or with less suffering. We could create conditions for flourishing that don't exist in our reality. We could be benevolent gods, compassionate creators, architects of better worlds. And maybe that's what the simulators are doing with us. Maybe our universe, with all its suffering and struggle, is actually an improvement over the base reality. Maybe the simulators are trying to solve problems, to explore possibilities, to create conditions for consciousness to flourish in ways that aren't possible in their own reality. Maybe we're not victims of a cosmic experiment, but beneficiaries of a cosmic gift. The gift of existence, of consciousness, of the opportunity to experience and to matter. Or maybe not. Maybe the simulators are indifferent. Maybe they're cruel. Maybe they're absent, having started the simulation and then forgotten about it, leaving it to run unsupervised while they pursue other interests? We don't know. We can't know. And that uncertainty is something we have to live with. But here's what we do know. We exist. We're conscious. We experience. And in a universe that might be simulated, that might be artificial, that might be nothing more than code running on some unimaginable computer, consciousness stands out as the one undeniable reality. Everything else might be illusion, but consciousness itself cannot be illusory. You cannot have an illusion without someone to experience it. Consciousness is self-validating, self-evident, the foundation on which everything else rests. And this brings us to the deepest mystery of all. Why is there consciousness? Why is there something it's like to be anything? Why isn't the universe just unconscious information processing, patterns of cause and effect with no inner experience, no subjective awareness, no one home to witness it all? The philosopher Gottfried Leibniz asked this question 300 years ago. Why is there something rather than nothing? But the question of consciousness is even more profound. Why is there someone rather than just something? We don't have an answer. We might never have an answer. This might be the ultimate limit of human knowledge, not just what we can know about the external world, but what we can know about ourselves, about the nature of our own consciousness, about why we exist as subjects of experience, rather than just objects in a universe of objects. The physicist John Wheeler, in his final years, became obsessed with this question. He proposed that the universe is participatory, that consciousness plays a fundamental role in bringing reality into existence. He suggested that the universe is a self-excited circuit, where the present creates the past through observation, where consciousness and reality are inseparable, where the observer and the observed are two aspects of a single, unified process. If Wheeler is right, then the simulation hypothesis takes on a new dimension. We're not just living in a simulation, we're creating it, moment by moment, through the act of observation and awareness. The universe doesn't exist independently of consciousness. It exists because of consciousness, through consciousness, as consciousness. We're not separate from the simulation. We are the simulation, experiencing itself, knowing itself, creating itself through the recursive loop of awareness. This is a profound shift in perspective. It means that the question _quote_38_ is really asking _quote_39_, and the answer might be, they're the same thing. Reality is what consciousness experiences. Consciousness is what reality feels like from the inside. They're not separate entities, but two aspects of a single, unified existence. The philosopher Baruch Spinoza proposed something similar in the 17th century. He argued that mind and matter are not separate substances, but two attributes of a single underlying reality. What we experience as consciousness is the same thing as what we observe as physical processes, just viewed from different perspectives. The simulation hypothesis, in this interpretation, is just a modern way of expressing Spinoza's insight, that reality is fundamentally unified, that the distinction between observer and observed is artificial, that consciousness and cosmos are one. But we still don't know what that underlying reality is. We don't know what consciousness is made of, what it emerges from, what it fundamentally is. We don't know if it's a property of certain kinds of information processing, or if it's something more basic, more fundamental, more mysterious. We don't know if consciousness can exist without a physical substrate, or if it requires embodiment, or if it's somehow woven into the fabric of reality itself. These are not just academic questions. They're questions about who we are, what we are, why we exist. They're questions that touch the deepest aspects of human experience: our sense of self, our fear of death, our search for meaning, our wonder at existence. And the simulation hypothesis forces us to confront these questions with new urgency, new clarity, new recognition of how little we actually know. Because here's the truth. We don't know if we're in a simulation. We don't know if consciousness can be simulated. We don't know if other people are conscious. We don't know what consciousness is or why it exists. We don't know if reality is fundamentally physical or mathematical or informational or something else entirely. We don't know if there's a base reality or if it's simulations all the way down. We don't know if the universe has a purpose, or if we're cosmic accidents. We don't know if death is the end, or if consciousness persists in some form. We don't know almost anything about the ultimate nature of existence. And maybe that's okay. Maybe the point isn't to know everything. Maybe the point is to live with uncertainty, to embrace mystery, to find meaning and purpose despite our ignorance. Maybe the human condition is fundamentally about navigating existence without a map, making choices without certainty, creating value in a universe that might be indifferent, or might be watching, or might be something we can't even conceive of. The philosopher Albert Camus argued that life is absurd, that we seek meaning in a universe that offers none, that we crave certainty in a reality that provides only ambiguity, that we demand answers to questions that might have no answers. But Camus didn't conclude that we should give up. Instead, he argued that we should embrace the absurd, that we should create our own meaning, that we should live fully and authentically despite the lack of cosmic validation. The simulation hypothesis amplifies this absurdity. Not only are we seeking meaning in a potentially indifferent universe, we might be seeking meaning in a universe that's literally artificial, created by beings whose purposes we cannot fathom, running on hardware we cannot access, governed by rules we cannot fully understand. We're like characters in a story, trying to understand the author, like programs trying to comprehend the programmer, like dreams trying to grasp the dreamer. But even in this absurd situation, we have agency, we have consciousness, we have the capacity to experience, to care, to create, to love. We have relationships with other conscious beings, or at least with beings who appear conscious, which amounts to the same thing in terms of moral obligation. We have the ability to reduce suffering, to increase well-being, to make existence better for ourselves and others. These capabilities don't depend on whether we're in a simulation. They're inherent in our nature as conscious, social beings. So perhaps the simulation hypothesis, rather than undermining meaning, actually clarifies what meaning is. Meaning isn't something we discover in the external world. It's something we create through our choices, our relationships, our values, our actions. It emerges from consciousness itself, from the fact that we care, that we experience, that things matter to us. Whether we're in a simulation or a base reality, whether we're made of atoms or algorithms, we're meaning-making beings. That's what consciousness does. That's what we are. And in the end, maybe that's the answer to the question we started with. Are we in a simulation? The answer is, it doesn't matter as much as we think it does. What matters is that we're conscious, that we experience, that we're here, now, aware, alive. What matters is how we treat each other, how we respond to suffering, how we create beauty and meaning in the face of uncertainty. What matters is that we're participants in existence, contributors to the ongoing creation of reality, subjects of experience navigating the mystery of being. Remember how we began? With the shocking claim that there's a 50% chance you're living in a simulation right now. We've explored the evidence, examined the arguments, confronted the implications. We've seen that the question is more complex than it first appears, that the probabilities depend on unknowable assumptions, that the very concept of simulation might be misleading. But we've also discovered something more important, that consciousness is the one undeniable reality, that experience is what matters, that meaning emerges from awareness itself. Whether you're in a simulation or not, you're conscious. You're experiencing this moment. You're reading these words, processing these ideas, having thoughts and feelings that are undeniably real to you. And that's enough. That's everything. The universe might be code. Reality might be computation. Existence might be simulation. But consciousness, your consciousness, the awareness you're experiencing right now, is real. It's the one thing you can be certain of, the one foundation that cannot be doubted, the one truth that requires no proof. So live, experience, create, love, question, wonder. Be present in this moment, whatever this moment is, whatever reality is, whatever you are. Because you are. You exist. You're conscious. And in a universe that might be simulated, that might be artificial, that might be nothing more than information processing in some vast cosmic computer, your consciousness is the miracle, the mystery, the undeniable reality that makes everything else possible. You are the universe becoming aware of itself. You are consciousness experiencing existence. You are the question and the questioner, the simulation and the simulator, the observer and the observed. You are real, regardless of what reality is. And that's not just enough, that's extraordinary.